All right, in this podcast, we're going to talk about both electron affinity as well as electronegativity. And if you were to look up affinity in the dictionary, here's what it says: a spontaneous or natural liking or sympathy for someone or something. So here we're talking about whether or not an atom or an ion likes or is prone to adding an electron. Does it want another electron? Okay. So one of the general ideas in chemistry is that, so let's do the reverse. So separating two things, taking an electron away from something, for instance, or breaking a bond, requires energy. You got to put energy in to pull something apart or to remove something. But combining things releases energy. And if I have an element and I add an electron, then that is combining things, and that will release energy. And anything that releases energy is going to be considered favorable, as opposed to things that require energy. This means it won't happen naturally. It's got to be done with some energy input to make it happen. Okay, so combining things release energy, which means electron affinity is going to be exothermic. So if I take fluorine and an electron, and that fluorine gains the electron, that will release energy to the system. Okay? Now the exception is if I try to add an electron to something that makes it more unstable. So you will see some electron affinity values, if you look them up, that are positive. And if it's positive, that means that is not going to happen naturally. So for instance, trying to add an electron to a very stable noble gas like argon is not something that's going to be favorable or happen naturally. It's going to require a significant energy input to make that happen. So the electron affinity for that process is going to be positive. Suppose you were asked for a value of the first ionization energy of a chlorine ion. What is the relationship between this quantity and the electron affinity of chlorine? So let's try to write an equation for both. So first, the ionization energy. So what that means is chlorine minus losing an electron. And if it loses an electron, it becomes chlorine plus that electron, right? And that requires some positive energy, some positive number of kilojoules. And the other electron affinity means I'm taking a chlorine atom and I am adding an electron, and that is going to give me a chlorine ion. And because I'm combining things, it's going to be a negative kilojoules. So how do you think those values, what this number is and this number is, how are they going to compare? Well, as it turns out, they are the same magnitude, the same number of kilojoules, but just opposite in sign. One requires energy, and the other releases the same amount of energy when it happens more naturally, more favorably. Okay. So trends in electron affinity. In general, electron affinity becomes more exothermic, because we know that fluorine, for instance, is more likely to pick up an electron than, let's say, boron or certainly lithium, which is more likely to lose, right? So as we go from left to right, electron affinity becomes more exothermic as you go from left to right. All right. And going down, if you look at going down a row, it's going to be less likely to take on an electron because it's further away from the pull of the nucleus. So the going down a group, the electron affinity will decrease. And we can see that here with these numbers. Okay. So based on these trends, what would you expect? Go ahead and answer that question. Which of these is going to have the largest or most negative electron affinity? Okay, welcome back. So let's take a look. Let's first identify what the elements are. We have potassium, we have sodium, we have silicon, and sulfur. So what we know is as we increase our nuclear charge going across, those atoms are going to have a higher effective nuclear charge and therefore be more attracted to the nucleus, more likely to gain electrons, and therefore it's going to be one of these guys on the right hand side, and it's going to be silicon, right? Or I'm sorry, not silicon, but sulfur. The sodium and potassium, very unlikely that it's going to gain electrons. Okay, so the answer here is sulfur. All right, let's talk about electronegativity. So electronegativity refers to the ability of an atom in a molecule to attract electrons to itself. So we're talking about two different elements that are forming a bond. Let's say we have element X and Y. So we're talking about that shared pair of electrons. So it measures how much an atom pulls on an electron in a bond. Okay? So here I have hydrogen and chlorine. So we're talking about this bond or this bond. And because chlorine is more electronegative, it's got higher, let's say, electron affinity, it's going to hold those electrons closer to itself. So more of that electron shared cloud is going to be around chlorine than it is hydrogen. Okay? So it's a relative scale. It was developed by Linus Pauling. And think about what element might have the highest electronegativity. All right, if you said fluorine, you were correct. It's got the highest electronegativity because, of course, it's the almost furthest to the right and near the top of the periodic table. The noble gases are not given values of electronegativity, and you can actually look at a table of electronegativities, and it's not anything that has units on it. It's just a relative scale. So what Pauling did was he established that let's give fluorine a value of 4, and the value of electronegativity for every other element is just a comparison to the value for fluorine. So we can see the electronegativity values as we go across. We're increasing our effective nuclear charge, and our electronegativity goes up. And of course, if we are increasing the number of shells, like we do when we go down a group, that electron is going to be further away from the nucleus and therefore have less pull from it. So across a period, we have higher Zeph. And if we go down a group, it's just further from the nucleus. All right, so here's the last question to see if you understand the idea of high electronegativity. What else would it mean? So think about this and then answer. Okay, so if you said high electronegativity would also mean, number 1, higher ionization energy. Again, it's higher electronegativity, higher effective nuclear charge, the same amount of shielding, right? And it's also going to be more likely to gain an electron. It's going to combine an electron and release that energy. Okay, so we are going to stop right there.